Okay, so we are working on chapter 10 and looking at respiratory system. And so when we take a look at the respiratory system, we're going to cover the anatomy and the physiology of the respiratory system and the function. So when we take a look at the respiratory system, essentially the respiratory system is looking at ensuring that you get oxygen in your body and that carbon dioxide exits your body. So you're taking in oxygen, getting rid of CO2, carbon dioxide, and a dual process, right? So inspiration, which is kind of the technical term for inhaling. So that basically means air is moving from the atmosphere into your lungs. And then expiration or exhaling is basically when we move air from our lungs out into the atmosphere. So here's kind of like the overall anatomy of the respiratory system. You can see here that you've got upper and lower respiratory. So the upper respiratory tract is associated with the nasal cavity. That's part of your respiratory tract, your pharynx, which is the technical term for your throat. And then, of course, your glottis. We learned about that one in the last chapter, where that closes off your trachea to keep food from going down your windpipe, and your larynx, which is essentially your voice box. We'll take a look at all those. And the lower respiratory, then from the larynx, it goes into your trachea. And then from your trachea, it'll basically bifurcate into two different areas in your bronchus, or your bronchial system, which are basically a series of tubes that will go into your lungs and fill your lungs up with air. This is all under the control, probably the most important muscle in the respiratory system, which is the diaphragm. Okay, so let's go ahead and take a look at the breathing mechanism. Ventilation itself, this is the cycle of inspiration and expiration, so inhale and exhale. Oftentimes, this is coordinated with and depends on the cardiovascular system, because after all, it doesn't help to bring in oxygen if you can't transport it. So basically, you make sure that you can transport oxygen through your cardiovascular system from the lung to the tissues. And then, of course, taking carbon dioxide from the tissues back to the lungs to be gotten rid of. And then, of course, on the inner portion, like at the cellular level, you have cellular respiration, which is basically where the cells are taking that oxygen, using it to make ATP. That's your energy that fuels your body. And then the waste product for that is carbon dioxide. And so that's basically how it kind of fits together, kind of in an interlocking way. So the first part we call external respiration. So this is basically the exchange of gases, oxygen and carbon dioxide, between the air in your blood, in your lungs typically, followed by the transport of those gases. Once you take in the oxygen from your lungs, it goes into your bloodstream and then out to the tissues. So that's basically transporting from the lungs to the tissues. And then internal respiration, which is the exchange of gases from between the blood and the tissues. And if you want to kind of add from the previous slide, cellular respiration, which is the intracellular usage of oxygen. And so that's how all of them are kind of connected in a large cycle. So kind of going back to our original image that we saw for the first time last time. So for the blood going from the heart is going to be basically moving from the heart, and the first stop is going to be in the lungs, where it's going to be exchanging CO2 and oxygen. So it'll be dumping off CO2 into the lungs and picking up oxygen from the lungs. And then, of course, it's going to be moving forward and then delivering that oxygen to the rest of the body. Okay. Now let's go ahead and start working our way from upper down to lower, and we'll take a look at all points of physiology and, of course, anatomy. So the upper respiratory tract we mentioned before is consisting of the nasal cavity. So that's actually what your nasal cavity is for. It's actually part of your respiratory system. And then the pharynx, which is the throat region. And then the larynx, which is your voice box. And so those are the main parts of your upper respiratory system, which you can kind of see here. So generally speaking, when you take a look at your nasal cavity is basically this entire large portion that's basically bounded by the upper region by your skull bones. There's kind of a roof up there. And the lower region is bounded by your palate, so the hard palate actually. And so between your hard palate and the skull bones is basically going to be this chamber, that's your nasal cavities. And so you got lots of mucous membranes in there, generating lots of mucus to filter out the air and to warm the air and so forth. In addition to that, of course, you also have pockets inside some of your skull bones, sinuses, basically, that we all kind of experience when we have allergies and things of that nature. And as we kind of start to move down from the nasal cavity, we move into the pharynx, which is your throat proper. And there's three different regions of the pharynx, basically where your nasal cavity meets the back of your throat. That is called your nasopharynx. And so this is basically just above where your uvula is. That's basically your little punching bag in the back of your throat that you see when you open your mouth. So just above that, on the upper portion of that, is your nasopharynx, and that's where the entrance point between your nasal cavity and your throat. As you move further down, directly behind your mouth is your oropharynx, oro for oral. So that's the part where you swallow and the food goes through your oropharynx. But notice when the food moves through it, it pushes your uvula up, and that closes off your nasal cavity, so you don't get food going up into your nasal cavity. And then your laryngopharynx, which is the portion below your epiglottis where you start to move into the larynx, and that's the portions of your throat. And then, of course, you have your glottis, which is the opening of the larynx, which is your voice box, and the epiglottis, which is the piece of elastic cartilage that closes off your trachea. So these are all the portions of your upper respiratory system. Now, beyond that, beyond the larynx, that starts to move into the lower respiratory system. So the nose is composed of the nares. That's the technical term for your nostrils. And so this is the entry point, the doorway, if you will, into your nasal cavities. And so as you inhale air, basically the air moves through past your nares into your nasal cavities. And so these are going to be separated. There's different subcavities within the nasal cavity itself that are separated by a septum of both bone on the upper and lower regions, and of course cartilage as well, which is a little softer. And it creates this kind of like layering system in your nasal cavity. So you'll notice you have these kind of layers here, which kind of look like stories. So those are the little layerings right there. And then in between each of those layers, you have these little passageways, these little thoroughfares. And so that's basically where the air moves through. You also have lots of hair in there to trap the particles that we inhale so that it doesn't get into our lungs, right? The idea is we want to clean up our air so we're not breathing in a bunch of particulate matter. Now, excuse me. Sorry, there's one setting I want to make sure I made before I move forward. So inside the nasal cavities, you're going to have basically mucous membranes, lots of mucous membranes. And so this is going to give you a kind of a sticky trap for these particles. So as the air passes by these mucous membranes, it's going to get stuck in that sticky mucus. And then you can move that mucus to the back of your nasopharynx where they'll be swallowed, or you can spit them out, expectorated. Basically, that's just spit them out or blow your nose, right? So that's basically what's happening. And you get constant drainage through the back of your throat all the time. Now, under that mucosal layer is what's called submucosa, which has a lot of capillaries. And these capillaries, because your blood is hot, will help warm and moisten the air, because the last thing you want to do is breathe in cold air into your lungs. That'll be a bit of a shock and it'll kind of be pretty painful. So you kind of warm that air. And so that's typically what allows us to get nosebleeds, especially at altitude, because a lot of times this is supposed to be a moist, warm area. And so if we breathe in a lot of cold, dry air, sometimes I'll dry up these membranes a little bit and cause rupture of these capillaries, which creates nosebleeds. So inside these nasal cavities, we also have receptors coming from our olfactory nerve that are essentially for odor. And so this is where we smell. So these receptors will pick up the different molecules in the air that will then allow us to be able to smell. We also have drainage in our in our nasal cavities for our tear glands. So the tear ducts actually drain into the upper portion of the nasal cavities. So the tear ducts will drain into those nasal cavities. That's the reason why we get all snotty when we cry. We also have a connection to the sinuses of the skull itself, right? And these sinuses will increase, obviously, in pressure as they fill up with fluid, and that'll create pressure headaches that we oftentimes feel right in between our eyes. That's our frontal sinus that's filling up there and causing us problems. Now, the air, as it passes through the nasal cavities, will be warmed up by those capillaries. Any molecules on there will be sensed by those odor receptors so that we can smell. And then it'll move into the nasopharynx, which is the upper portion of the pharynx just before you get to the uvula. In addition to a connection between your nasal cavities and your nasopharynx, you also have a connection at this point between your auditory tubes, your eustachian tubes, that connect your middle ear to your nasopharynx. So this is one of the reasons why our ears get plugged up when we get sick. So we get lots of bad congestion. Sometimes our ears will kind of get all plugged up, and that's because the eustachian tubes are getting plugged up. They're supposed to drain any fluid in the middle ear into our nasal cavity. So you can kind of see now the nasal cavity is kind of like an overall, just sort of like a drainage ditch, right? So you're draining a lot of different things into your nasopharynx. And so when you go into altitude, like when you're going up into the mountains, a lot of times what will happen is these eustachian tubes have air in them usually. And the middle ear is mostly air, but there also can be liquid and fluid in there as well. But as the outer pressures change, your inner pressures in your middle ears have to equalize to that pressure. And so what happens is you kind of get this popping sensation. And so that is your kind of body sort of adjusting to that change in pressure in the eustachian tube. So basically communicating through these little openings to your nasopharynx, that feeling of that kind of popping or like your ears opening up. So that's kind of what's happening with pressure. Now let's kind of keep moving down the pharynx. So where the pharynx is your throat. So it's kind of a funnel shaped thing where it's large at the top of the nasal side of things. As it moves from the oral pharynx to the larynx, it kind of gets tighter and tighter and tighter, right? So you have your nasopharynx, you have your oropharynx, and your laryngopharynx. This is basically where your tonsils are, right? So your tonsils, remember, are lymphoid tissue. We covered that one in chapter 7. And typically they're sitting right at the confluence of your oral cavity and your pharynx. So right behind, right where it gets to the backside of your throat. And this is basically because this lymphoid tissue is part of your immune system, is part of your defense against pathogens. And so those are your main tonsils. You also have another set of tonsils that's up further in your nasopharynx called the adenoids. And those are to basically do battle with any pathogens that you might inhale through your nasal cavity. So now that's the oropharynx. Now, as we start to move down into the larynx, I mean, the larynx is basically a cartilaginous structure. It's actually the beginning of the trachea. So it's basically where the pharynx and the trachea meet. If you want to know where your larynx is, basically it's your Adam's apple. That's actually what's called the laryngeal prominence. It's actually a large piece of cartilage. That covers your larynx. And so that's basically where that is. That's basically your thyroid cartilage, just right around that area is where your thyroid is as well. So that's protecting your larynx. Now in your larynx, what you're going to see is vocal cords. So this is where your voice is. And so typically what you have in terms of your vocal cords, they're kind of organized like strings. They're a little bit of a combination of mucosal folds. That's to give it suppleness, just to make it supple, along with elastic ligaments, right? This gives it flexibility. And so ultimately what happens is you kind of have this split between the vocal cords And that split or that opening is what's called the glottis, right? And so as air passes through the glottis, it's going to cause those vocal cords to vibrate, producing a sound. So for those of you who are wind instrument aficionados, the double reed instruments like oboe, which is one of the ones I play, and bassoon and other types of things have this same exact set of physics. Instead of one reed that vibrates like you saxophone players, an oboe, a double reed system has a double reed. So there's a piece of a reed on the top, a piece of a reed on the bottom. And then what you do is you put your lips on top of each reed and you blow into the hole. And the hole will cause the reeds to vibrate. That's my little sign for vibrating. It looks like an eyeball, right? And then as they vibrate, they'll basically kind of they actually won't create sound, but they can create sound. So those of themselves can create sound, but they create sound with the reinforcement of the sound going through the holes of the wind instrument itself. So it's the same basic idea. It's kind of like vibrating guitar strings. So ultimately, the tighter the tension of the vocal cord, usually the higher the pitch, just like with a stringed instrument, right? The tighter it's wound, the higher the pitch. The lower it's wound, the less tension in there, the lower the pitch. So if you open up that glottis and it's wider in nature, then your pitch tends to be on the lower side. Really clamp on that glottis and make it a very narrow sort of a thing, then the pitch tends to be higher. Very similar to the way you whistle. Right? If you kind of pinch down on the hole that you create with your lips, you get a higher tone. You open it up a little bit, relax your lips, and you get a little lower tone. And so the loudness, typically of your voice, will depend on the amount of vibration that your vocal cords will experience, plus the amount of air. So your base of your tongue is up here. So this kind of gives you orientation here and what we're talking about. And then the opening here is going to be your glottis. That's basically where you're going to be blowing the air through. The epiglottis is going to be, or the base of the epiglottis, which you can see here, is going to be this piece of cartilage here. That's the one that's closing off your trachea so that you don't inhale food. And then your vocal cords, you can see their membranes, but then there's this little sharp band right here, which acts like guitar strings, that you can cinch down on that opening glottis. So as you vibrate the vocal cords, then you're going to create sound. And so when you swallow food, and we already mentioned this before, so I don't want to belabor this point and move quickly past it, right? Basically, what's going to happen is your larynx is going to move upward, and so it's going to push against the epiglottis, and that flap of tissue will essentially close over the larynx and the trachea, causing it to shut off. So you're not inhaling your food. And that's the reason why you can't sing or talk and swallow at the same time, because you're fundamentally shutting off one system while you're doing the other. Okay, now let's take a look at the lower respiratory tract. So the lower respiratory tract is going to be composed of the trachea, the bronchial tree, which is mostly in the lungs, and then, of course, the lungs tissue itself. So let's take a look at the trachea. This is basically the windpipe. Okay, so it's that large structure in the front of your neck with those kind of ribs on it just below your Adam's apple. And so the larynx, after you leave the larynx, which is the entrance to the respiratory system, the lower respiratory system, that's only air passes through the larynx. Then you're going to move into what's called the primary bronchi, okay, or the main. And the walls of the trachea are going to be covered by these C-shaped cartilaginous rings. And that's what the rings are on the front of your trachea. When you feel your trachea, the rings are tracheal cartilage that basically keeps your trachea from collapsing. So you keep that windpipe open at all times. And so because you have cartilage holding over your windpipe, you can swallow and your esophagus can poof out and expand as food goes down it without worrying about cutting off your trachea, because your cartilaginous rings are going to keep your trachea open. And so here's kind of what it kind of looks like in terms of the cell lining. And we're going to take a look at that here in just a second. So I'm going to go back to that slide here. But when you take a look at your trachea and pretty much your respiratory system in general, it's going to be lined with a special type of epithelial tissue called pseudostratified ciliated columnar epithelium. And so we talked about this one before in the tissues chapter, but these are the ones that have what's called goblet cells who are busy secreting mucus. So they produce mucus. And as it produces mucus, just the same when your nasal cavity, the mucus is trapping particulate matter, it's also trapping debris here as well. And so in this case, what happens is when you get this mucus that's been trapped and been trapping debris, then your mucus is going to be swept up from your lungs toward your larynx, toward your pharynx, and the cilia are the ones that are doing this. And then what's going to happen is you're going to cough it out. So that basically ensures that the air that you're breathing in is going to be doubly clean. So you caught a lot of those particulate pieces in your nasal cavity. As you breathe in, the mucus in your tracheal lining is also trapping more particles. So the idea is that the air that gets into your lungs is going to be as clean as possible. This is one of the reasons why smokers have that really strong smoker's cough, is because they're constantly bombarding their respiratory epithelium with particulate matter. And eventually, at some point, this will damage the cilia and it'll cause a lot of lung issues. They'll have a lot of buildup of mucus in their lungs, and just things go south from there. So this is what it looks like. So here's your ciliated columnar epithelium. So you can see you have basically your basement membrane down here. And you have your long columnar cells. And of course, you can see your big globules of mucus. So that's basically what these big globules are. By the way, if you notice, this from up here is basically a cartoon. From here down is actually a micrograph. So this is actually the real thing. So you can see these balls of mucus that are being secreted. So you create this like little stream of mucus on top, and it traps these little particles, and the cilia will basically sweep it up toward the lungs to cough it out. The ostomy basically is when you put a breathing tube in, is typically inserted into the trachea. So you make a puncture in the trachea and you insert a tube so that you can breathe directly from into your trachea. So you bypass the nasal cavity. Now let's take a look at the bronchial tree. That's the next stop, right? So basically we had the main bronchi, the primary bronchi, which is essentially where the trachea splits. It'll split into two halves, one leading to each side of the lungs, right and left lung. And so from there, the primary bronchi will branch into what's called secondary bronchi. And they'll continue to branch until they're small, like a bronchiole, which is about 1 millimeter in diameter. And so like the trachea, bronchi typically have cartilage, but as it gets smaller and smaller, that cartilage will disappear. So those bronchioles don't have cartilage around them, but the larger bronchi do. So in an asthma attack, what's happening? So there's smooth muscle around your bronchial vessels, your bronchioles in particular, these are the smaller ones. So what happens is the smooth muscle will start to constrict. And as you constrict, it causes wheezing. And that constriction is basically caused by some sort of an agent. Like if it's allergy induced, it's some sort of an allergen response. And so that causes that wheezing. So you take an inhaler to relax those smooth muscles and to dilate those bronchioles so that you can breathe easier. Now, the bronchioles themselves are going to be leading into the lungs and the lung tissue that terminates into these air sacs called alveoli. And so it's alveolus for short. And here's what it looks like. So here, basically, you can see your bronchial tube that's leading into this little cluster of air sacs. And each one of these air sacs is going to be an alveolus. And the alveolus basically fills with air. And it exchanges oxygen and CO2 with capillaries from the blood. And so you can see all these capillaries wrapped around each alveoli. That's where your gas exchange is happening. And you typically have a cluster of alveoli, kind of like a little cluster of grapes. And that's kind of how they work. So it's a very vascular area when you're talking about your alveolar sacs. So the lungs then, that's the bronchial system. Now let's get to the lungs. The lungs basically are generally made up of your secondary bronchi, or that's a branch off of the primaries, and your bronchioles and your alveoli. That's basically what's inside your lungs. You have two different lungs. You have the right lung, which has 3 lobes, and you have the left lung, which has 2 lobes. And the reason why it has 2 is because it has to kind of get out of the way to make room for your heart. So you can't have 3 lobes on the left side because of your heart. Now, each lobe itself is subdivided into lobules. These are smaller portions, smaller regions. And of course, you have to subdivide your bronchioles into each of those lobules. This is the reason why it keeps dividing and dividing and dividing and dividing. Now, you enclose each lung in the pleura, right? So this is the pleural cavity. So they inhabit the pleural cavity, and so they're covered by that serous membrane. You have your pleural cavity, which is lined by your parietal pleura, and you have your visceral pleura, which is laying on top of the lungs itself. And in between, you have a cavity which produces and contains the serous fluid. So there's fluid actually in the cavity between your lungs and the wall of your lung cavity. So the pleural fluid itself that's in the cavity has a sense of surface tension, and so it'll tend to stick to the parietal layer, and that's the layer that sticks to the cavity wall, and the visceral layer, which is the one that's actually attached to the lung surface itself. And so this surface tension, when your thoracic cavity enlarges, for instance, as you're inhaling, this parietal pleura will basically pull on that visceral pleura and cause the lungs to expand outward. This increases the size of the lungs. Okay. Now, what happens if you have an inflammation of the pleural linings? That's pleurisy. And that'll create, oftentimes, that's very painful, it'll create a lot of fluid, a lot of pressure buildup, and that usually hurts pretty badly chest-wise. Now let's go ahead and get down to the alveoli, right? So this is kind of our last bottom portion of our flow chart that we had earlier. And so you have a lot of alveoli. These guys are the important areas, right? These are the physiological hotspot. This is where all the magic is happening. So as a result, you have a lot of alveoli, hundreds of millions of alveoli. And each sac is surrounded by a lot of capillaries so that you can get exchange. Now remember, the walls of your alveolar sac and the capillaries are very, very thin, right? So this is a very thin membrane. And this is to ensure exchange. You want good, efficient exchange. So you have a very thin membrane. And this gives you gas exchange between your alveoli and your capillaries. Generally speaking, oxygen will move across the alveolar wall by diffusion. It'll enter into the bloodstream. Carbon dioxide also diffuses, but this goes from the blood into the alveoli. And the alveoli on the inside are actually lined with a thin film. It's a lipoprotein film. It's a lipidy type of a film called surfactant. And what this does, it lowers the surface tension of water, and this prevents the alveoli from closing. So what will happen is they'll stick. They'll stick closed, like a water balloon. So to keep your alveoli from collapsing and not being able to open again, then you reduce that surface tension so that your lungs can open up easily and nicely. So respiratory distress syndrome typically is when infants don't make enough surfactant and those alveoli collapse and they have a hard time taking in a breath. And so it's a little tricky. So we have to kind of force air in there in order to get them to open up and breathe. Okay, so let's take a look at our two phases of ventilation. We have inspiration and expiration, basically moving air into the lungs versus moving the air out of the lungs. When you take a look at ventilation, we have to kind of cover a couple of things. First of all, number one is the air that we're breathing in is a continuous column, right? So it's not just batches, it's a continuous column, typically going from the pharynx all the way to the alveoli of the lungs. So we need to understand that there's air inside our body that's even not in our lungs, right? So there's air in our trachea still, there's air in our nasal cavity, there's air in our throat. And so it's a continuous column of air. So we need to understand that one. And we're basically pulling that column down into the lungs and pushing it out of the lungs, kind of going back and forth. And that column of air is interconnected with the atmosphere, the air in your atmosphere. So the lungs themselves are within your sealed thoracic cavity, right? The pleural cavity. And that itself is basically bounded by your rib cage, which essentially covers your thoracic cavity and provides for protection. However, in between your ribs, you have muscles called intercostal muscles. This basically will allow for expansion of your chest. And then, of course, you have the diaphragm, which is the floor of the thoracic cavity, and it marks the boundary between your thoracic and your abdominal cavities. So then the lungs, which are adhered to the thoracic wall by the pleura, basically the space in between them, right? That intrapleural space is full of fluid, pleural fluid, right? This is that viscous stuff that pulls on the visceral pleura. It's not a very big space. It's a very small space, but it's filled with fluid, and that's a viscous fluid. So it pulls on that visceral portion. The other thing we need to understand in terms of ventilation facts is because we're dealing with gases, they obey gas laws. And so basically there's a couple of gas laws we need to understand. The first one is called Boyle's law. This is something oftentimes you'll learn about in chemistry, but we need to learn it here in order to understand the mechanism of breathing. First of all, what Boyle's law states is that when you have a constant temperature, the pressure of a given quantity of gas is inversely proportional to its volume. That is to say that as volume goes up, your pressure goes down. For instance, if you kind of drew a picture of this, if I have a large volume versus a small volume, and I have gas in this large volume, and I have the same number of gas molecules in a small volume, then this would represent the high volume, this would be the low volume, but because there is a lot of space to spread out, it's low pressure. So there's not a lot of molecules bumping into each other. Whereas in the small volume area, they're bumping into each other. They can't get away from each other, and so it's high pressure. So Boyle basically says that as your volume that contains the pressure increases, your pressure drops. Okay. And that's basically what he said. Now, this is important, especially when it comes to inhalation and exhalation. So let's take a look at this. And this is kind of like, just kind of follow me on this one. It's a little bit of kind of an illustration and kind of the mechanism of it. So basically, if your pressure, in this case, the sides of the container move outward, basically that means your volume is dropping. Then what's going to happen is your air pressure is decreasing. Your volume is getting larger. Excuse me, I got that backwards. So you're getting larger because your walls are moving outer, so your volume is going up, but your pressure is going down. Now, as your container moves inward, your volume now is dropping, and so your pressure is going up. So you notice the inverse proportion. That's what Boyle's saying. So now with those facts, let's go ahead and take a look at the mechanism of inspiration and expiration. thing is inspiration, always to understand, is an active process. That is to say that in order to inhale, all you have to do is contract your diaphragm. So basically, this is caused by contraction of your diaphragm. And of course, your external intercostal muscles. You have two sets, internal and external. And so the diaphragm, in its relaxed shape, is a dome-shaped sort of thing. When it contracts, it basically pulls downward and flattens out. And as it does so, as it pulls downward, it pulls on the lungs. So contraction basically will, because it's all interconnected, will basically cause your rib cage to move upward and outward. But ultimately, what's going to happen is the diaphragm pulls down on the thoracic cavity. So basically what you have in your thoracic cavity is you have basically kind of a downward pull, you have an outward expansion, and you have an upward lift in your rib cage. Now the downward pull is the diaphragm. That's the one who's pulling down and opening things up. The outward expansion are your costal muscles, your external costal muscles. That's your the muscles in between your ribs. And the lift up is due to a group of muscles called scalenes, which are all connected right here at the top, lifting your rib cage up to expand your rib cage so that your lungs can expand inside. This increases the size of your thoracic cavity. And by the way, if you're keeping track, what we mean by that is this increases the volume. Boyle's law, we know what happens when you increase volume. When you increase volume, what's going to happen is your pressure goes down, right? So basically your thoracic volume increases. So you have an increase in volume at this particular point. The lungs will also increase in volume. This is because the lungs are kind of adhering to the thoracic cavity wall. And then as your lung increases, the air pressure decreases. That's the air pressure in the alveoli. Now what you have is you have a low alveolar pressure. So I'm just going to note that as the alveolar pressure. I'm going to note as pressure ALV, as opposed to the atmospheric pressure, which I'm going to say is pressure ATM. So what happens is the alveolar pressure is now lower than the atmospheric pressure. And typically speaking, you always flow from high to low. So this would be a high gradient in the atmosphere. This would be a low gradient. And so air would then move from outside, moving into the body itself. So you're going to get contraction as the diaphragm moves down. It's going to basically pull the lungs open from the bottom. Your external costals will expand outward and then up with your scalene. And then that'll increase the volume of your lungs, which will allow air to flow down its pressure gradient into each lung, filling your alveoli with air. That's inspiration. Now, expiration is a passive phase. So it's associated with the relaxation of the diaphragm. So at this point, the diaphragm and the intercostal muscles are just relaxing. The rib cage will basically move back to its normal position. The lungs recoil. The air pressure inside increases, and so the air flows outward. So what keeps the alveoli from collapsing is a surfactant. So even though the alveoli are draining the air out, they don't stick together because of the surfactant. And so ultimately, as the lungs recoil, the pressure that's between the pleura and the cavity allows you to keep those alveoli so they don't fully collapse. When you puncture a lung, right? Basically what happens is you have air that enters that cavity area, causing that sort of system of pulling to sort of malfunction. And it makes it harder to open your lungs and to breathe. This is what exhalation looks like. As your diaphragm relaxes, it's going back up, making the volume here smaller. which increases the air pressure inside. So at this particular point now, what happens is your alveolar pressure is now greater than your atmospheric pressure. And so you're going to have to flow from high to low, which means you're going to now flow out of your lungs into the air following the pressure gradient. So then when you take a look at inspiration and expiration, you have a maximizing, you have a normal at rest piece and you have a maximizing piece, right? For instance, you can breathe hard with maximum inhale. You can use your back muscles, your chest muscles, your neck muscles. I mean, you can really deploy a lot of other muscles to kind of help really open up your lungs and to increase that size even more so, more dramatically. Expiration can also be forced, right? For instance, singing, talking, just blowing out air, that's all forcing your body. So what happens is you contract your internal intercostal muscle, and this will kind of squinch down, that's the technical term, squinch down on your rib cage, squeezing out all the air out of your lungs. You can also use your abdominal muscles to contract, and they'll kind of push upward, pushing up against your diaphragm, forcing the air out as well. So you can force things in and out. Now let's take a look at the exchange of air, basically into and out of. So we have a couple of different types of volumes, what we refer to as capacities. The first one we're going to run into is what's called tidal volume. Tidal volume is basically the amount of air that you breathe at normal rest, right? So you have a normal sort of in and out. This is basically your tidal. So you breathe in, certain amount, you breathe out. You breathe in, you breathe out. You breathe in, you breathe out. So there's a tidal volume there. Then vital capacity is basically the total volume that you can get from the very top of your breath to the very bottom of your breath. So this is the maximum amount of air moved in and out by one breath. So for instance, if I were to tell you to go up to the very top of your breath, you would come way up here, right? And then if I tell you to exhale right after that to the very bottom of your breath, you come down here. That from here to here is going to be your vital capacity, okay? And so that's what you can get from the very top to the very bottom of your breath. That's composed of two different pieces called inspiratory and expiratory reserve volume. Reserve because it's extra amount of inhale that you can do above your normal tidal breathing. For instance, from the top of your tidal to the top of your very top of your breath, this is your IRV, your inspiratory reserve. It's the extra amount of breathing that you can do when you want to breathe deep. And then your expiratory reserve is the extra amount that you can exhale on the bottom as you want to exhale down to the very bottom. Basically, vital capacity is the sum of IRV, your total volume, plus your expiratory reserve. That's your vital capacity. So we have a couple of others. Of course, you have stuff that you can't get to. That's residual volume, right? So regardless of how far down the bottom of your breath you can go, that's your residual volume, the stuff you can't get to. And the lump sum total of everything is what we refer to as total lung capacity. And sometimes we'll measure that as well. A lot of the air that you breathe, not a lot of it, I mean, some of it, will never actually get to the lungs, right? So basically, it's still trapped in our nasal cavity, it's in our trachea, it's in our bronchi, it's in our bronchioles. But these are not for gas exchange. This is what's called dead airspace, right? So basically, the only place of gas exchange is occurring in the alveoli. So all the rest of the air that's not in the alveoli is what's called dead airspace. And so a lot of that residual volume is this remaining air after exhalation. Okay. Let's go ahead and let's take a look at control, right? Because we can control our breathing either by nervous means, by our nervous system, or by chemical means as well, by our endocrine system. And we take a look at our nervous control. We have in our brain, typically in our brain stem, respiratory control centers. These are regions of our brain that are designed essentially to automatically regulate our breathing. And so these are the ones that are sending signals to our diaphragm to contract every so often. They're also sending information to our external intercostals to expand our rib cage, causing inspiration to occur. And so oftentimes when you are breathing in, the nerves will fire. They'll send nerve signals to the diaphragm But then when you exhale, there's no nerve signal being sent, right? So exhalation, because it's a passive process, no nerve signals are sent, allowing the diaphragm to relax. And inhalation, nerve signals are sent, stimulating diaphragm contraction. That's kind of what the nervous hookup looks like. So basically from your respiratory center, you have all these different motor pathways that are basically going to the different regions of the lungs. So the inspiratory stuff is stuff over here on the left side. Expiratory stuff is stuff on the right side. And so you have motor pathways that come from your respiratory center, from your brain, that will then communicate. Notice how these neurons are connecting to each other. And one of them, your phrenic nerve, is going down to your diaphragm. Notice all the different nerve connections here in your diaphragm. So it's communicating your diaphragm to contract. Also, there's a major conduit that's communicating to each of those external intercostals to basically get those guys to fire up so that they can expand out. On the expiration side of things, you have the vagus nerve. And so this basically is, there's no stimuli coming here. Here, basically what's happening is you have sensory information. You have stretch receptors that's kind of communicating to your brain when your lungs meet max capacity. It's kind of like a stretch field. Kind of when you're blowing up a balloon, you realize that you're getting close to the end because of the stretch, the amount of stretch in the balloon. You don't want it to pop in your face. Same kind of idea is happening here. You get stretch receptors sending their signals to the brain to say, listen, we're pretty much done here, so you got to stop. So when you have SIDS, typically, which is sudden death syndrome, this is an infant, usually under a year old, and it seems fine. Everything's good, sleeping well, and so then all of a sudden the baby just stops breathing. We don't know why SIDS happens really, but it's not a vaccine thing. It's not vomiting. It's not infections. So those have all been ruled out. Basically, we're probably thinking the baby's nervous systems are heavily developing earlier on. And so it could be that what happens is a misdevelopment or miscommunication between the respiratory center of the brain and the lungs. So it's basically a misfire, essentially, that happens to be a catastrophic misfire, and the baby just simply stops breathing. And so normally what happens is the respiratory center, which typically is automatic, right? So it's sending these controls, will regulate both the rate and the depth of breathing. Right. And so, and that's kind of automatic. So that's just your normal tidal flow. You're just kind of going back. But you also have voluntary control of your respiratory system because you can breathe, you can change your breathing patterns, right? For instance, when you're speaking, your breathing patterns are different than when you're singing and eating, swimming, and so forth. And none of that, but you can force inspiration. So if I wanted to inhale strongly, I could do that. Right? My stretch receptors would basically tell the rest of my brain this is when to stop because we're at the end here. And so that would be communicated to my respiratory center, and that would kind of create this stoppage, if you will, this arresting, so that we don't overstretch the lungs. We don't want to pop our lungs. That'd be a bad situation. Now, what about chemical control? Right? We talked about nervous control. What about chemical control? Well, chemical control basically is associated with different types of chemical receptors. For instance, oftentimes what will happen is CO2 as a byproduct will be made by cells during cellular respiration. It enters the blood and it combines with water to form our carbonate buffer system, but it creates acidity. And we have special sensory receptors in the body called chemoreceptors, and their job is to sense the acidity. It sense the acidity of your body, acidic condition, chemical composition of your body fluid. And so when they sense this, then they'll communicate that to your brain. So you have two major sets of chemoreceptors that are sensitive to pH and also oxygen and CO2. Now, when these guys sense pH, they can speed up breathing to eliminate CO2, which causes the acidity. So one set of these is in the medulla oblongata, which is where your respiratory center is. Right. The other one, there's another set in the carotid bodies and your carotid arteries that are taking blood to your head, and the aortic bodies, which are in the aorta, which are taking blood to the rest of the body. So these basically will respond to carbon dioxide levels in the blood and also pH levels, and they'll basically communicate with the respiratory center to help you regulate the amount of CO2 that's building up in your system. Too much CO2, then it'll stimulate those receptors, and then those receptors will communicate to the respiratory centers to increase breathing so that you can eliminate more CO2 and bring your pH back down to normal levels. It's all about homeostasis, right? So ultimately, your pH will decrease, becomes acidic. The respiratory center will increase the rate and depth of breathing, allowing you to eliminate that CO2, which is pretty much is what I just said and on this entire slide. And that basically allows you to increase your pH and regulate your pH levels. When you hold your breath, what happens is CO2 begins to accumulate in the blood, decreasing the pH. The respiratory center will be stimulated by the chemoreceptors and ultimately will override your voluntary inhibition. So you can't actually hold your breath forever because your respiratory centers will eventually hit a kind of a critical mass, and then what they'll do is they'll override your voluntary situation, and they basically say, nope, you're going to go ahead and breathe. Okay. So now let's go ahead and take a look at gas exchange in the body. So now we're going to be taking a look at oxygen, which is needed for cells to make ATP through cellular respiration. And that's going to allow you to fuel your cells with the energy they need to do their job. So once you get that CO2 built up, then you have to exchange that CO2 for oxygen. And so it's kind of what it looks like. So from the lungs, what you have basically is you have oxygen that's coming into the red blood cells. And not only that, but on the same side, you have carbon dioxide that's leaving the red blood cells and going into the lungs so that you can breathe out. Then newly oxygenated blood is going to be delivered throughout the rest of the body. Where at the tissues, what's going to happen is the reverse. So the blood's going to deliver that oxygen to the tissues who are going to consume it, and they're going to create a byproduct, CO2, and that's going to be picked up by the red blood cells. And then that's going to be taken back to the lungs for exchange again. And that's basically how the respiratory system works. So when you take a look at gas exchange, essentially gases exert pressure, right? And so the amount of pressure it exerts is what's called a partial pressure. So for instance, we usually call that PCO2 or PO2 subscript. This is the amount of pressure that's created by CO2 itself. This is the amount of pressure that's created by oxygen. Ultimately, the partial pressures of these gases will differ across the membrane. So for instance, if it's a high pressure, it'll diffuse always from high to low. This is the reason why atmospheric pressure or atmospheric air comes into your lungs when you increase your volume, because you create a pressure gradient. Okay. Now, external respiration, we already talked about, right? You're bringing air into your lungs, into your alveoli, exposing it to your blood capillaries. Typically speaking, in the capillaries, in the blood, your PCO2, your partial pressure of CO2 is higher. So it's going to move from high to low, which means it's going to move out of the blood into the lungs. Now, typically speaking, at the same time, your partial pressure of oxygen is higher in the alveoli than it is in the blood. So it's going to flow down its gradient, and it's going to go into those capillaries. So this is basically what they're doing. They're going to follow their pressure gradients. Okay. Now, when you take a look at how CO2 is carried throughout the body, most of the CO2 is carried in our carbonate buffer system as a bicarbonate situation. So for instance, if you take water and CO2, it naturally will combine through carbonic anhydrase into carbonic acid, which will dissociate into your hydrogen ion, creating acidity, and your bicarb as well. So you can back these up and sort of move these back and forth. You store a lot of your CO2 that you create in this carbonate system. This is your carbonate buffer system. That creates your physiological pH of 7.4. And so if you have a low atmospheric PCO2, it basically moves to the right. right? So it's going to move in that direction. Okay, so carbonic anhydrase is basically the enzyme that will essentially facilitate the breakdown of carbonic acid into the acid in the red blood cells. When you hyperventilate, that's basically breathing at a high rate. What happens is you're pushing this reaction to the right. So you're getting rid of a lot of CO2, causing the reaction to move to the right. And so as a result, you have fewer hydrogen ions, which is alkalosis. So basically becoming too basic. Not enough CO2 in the system. Hypoventilation is breathing at too low a rate, basically moves it to the left, right? So now you have too much hydrogen ion. It's becoming too acidic. That's acidosis. And so both of these are controlled by just changing your breathing rates. Now, when you take a look at your pulmonary capillaries, these are the capillaries that are wrapped around the alveoli. Essentially, the air has a higher partial pressure of oxygen, so it diffuses into the plasma and then into the red blood cells. Now, this is where hemoglobin comes in. So the hemoglobin inside your red blood cells is essentially what binds to the oxygen. So for instance, you have deoxygenated hemoglobin, which will get your oxygen by diffusion, and it'll bind to it to create oxyhemoglobin. And then this will basically be delivered to the tissues. Now, in internal respiration, this is the exchange of gases between the blood and the systemic capillaries to get to the tissue cells. What happens is your hemoglobin will come to the tissues, and then what will happen is the pressures will change, so it'll force hemoglobin to give up its oxygen, and then it goes into the tissues. And it's following its pressure gradient. And that's basically it. So notice it's a pressure gradient sort of driving a lot of this, right? So ultimately, oxygen will diffuse out of the blood into the tissues because of that partial pressure of oxygen is lower, so it's flowing down its pressure gradient. Carbon dioxide will diffuse into the blood also because of its pressure gradient. And so this is what's being produced by cellular respiration. So both of these gases are simply following their respective pressure gradients. That's the key piece. So the key piece to this that unlocks it all is the pressure gradients. So now let's go ahead and take a look at kind of the last little bit here that we have, or the last couple of things here. Upper respiratory tract infections, right? So basically, when you take a look at this, they start oftentimes in the nose. They can move through the nasal cavities, into the pharynx, that's sore throat, larynx, sinuses, middle ears. They can get down into the chest itself. And so this is oftentimes viral or bacterial in nature. And so that's because this is where you're actively filtering out those pathogens. If they kind of lodge in there and they start to breed, then they start to create situations like colds, for instance. That's adenovirus. This is where you're getting sneezy, runny noses, sinusitis, which is basically an infection and blockages of the sinuses, frontal sinus, things like that. Tonsillitis is an inflammation of the tonsils. So oftentimes this happens too often. You'll have to have them surgically removed because they block the throat and can make it dangerous and hard to breathe. And of course, laryngitis is basically infection of the larynx. Oftentimes this leads to funky business in your voice. So your voice kind of gets lower and kind of gets lost and things like that. Lower respiratory tract. So you have infections that can happen down there in your lungs, restrictive pulmonary disorders, obstructive pulmonary disorders, lung cancer. Those in the lower respiratory system, they're usually pretty severe, right? So you don't want lower respiratory diseases. For instance, you have acute bronchitis, which is essentially the infection of your primary and secondary bronchi. So you don't want that one. Pneumonia, which is typically a bacterial and viral infection of your bronchi, it causes alveoli to fill with thick fluid. Basically, it disrupts gas exchange. So you're not able to exchange gases as efficiently, and you kind of suffocate. Basically, you drown essentially on your own fluids. Tuberculosis, we talked about earlier, it's a bacterial infection that leads to those hard tubercles, those nodules, and creates a lot of problems. This is kind of what it looks like. This is what the different diseases look like. So you can see pneumonia, basically your alveoli are filling up with fluid as if you were breathing in water. In pulmonary fibrosis, you get actually connective tissue fibers that basically create blockages in normal breathing. Tuberculosis creates these hard nodules that interferes with breathing and exchange. Emphysema, the alveoli burst, and so you can't actually get decent exchange because you're damaging the alveoli. And asthma is basically constriction of your passageways. So you have to relax that smooth muscle. And then bronchitis, you basically have a liner disruption, oftentimes with a lot of fluid mucus being developed there as well. In restrictive pulmonary disorders, you typically have a vital capacity reduction. So basically, the lungs have lost elasticity. They're not able to expand and contract as well. Like with pulmonary fibrosis, that's a blockage. The connective tissue that builds up in there and eliminates the ability for it to properly expand and contract. Obstructive pulmonary disorders, typically, this is where your air is not flowing freely through the passageways. For instance, chronic bronchitis will cause this. Emphysema will cause this. Asthma will cause this. These are all collectively referred to as chronic obstructive pulmonary disease, or COPD. And they tend to be chronic and recurrent. And then, of course, you have chronic bronchitis, which is your inflamed passageways that constantly get inflamed, and it irritates the mucus, so they overreact. And so as a result, you'll kind of get a thick mucousy discharge in all of this. And then over time, chronically, they can degenerate, and this could cause problems. So for instance, smoking is a common cause of this, or being in an area with lots of pollutants. If you live near lots of forest fires, you can cause a lot of this sort of issue. Emphysema, basically, this is basically where you actually damage your alveoli, right? So you damage your walls of your alveoli, and basically it eliminates to exchange gases. So you have less oxygen because you have less functional surface to actually exchange. And so emphysema is just basically like a slow suffocation is what it is. So you're not able to actually absorb as much oxygen. It can't diffuse across the membrane because it's damaged. And so what happens is it's oftentimes is kind of like a constant, it's like a growing hypoxia. And a slow suffocation. You simply just aren't getting enough oxygen. You're breathing, but you're not getting enough oxygen. It's just not crossing your membrane. And so, so sometimes you can do lung transplants in some cases. So LVRS, this is basically where you kind of take a little bit of normal tissue and you add it to the diseased tissue to give you a little bit more lung capacity so that you can breathe a little bit better. And then, of course, asthma, essentially wheezing, breathlessness, things like that. Oftentimes, it's an allergenic sort of a thing. It can be also tobacco smoke in general, but basically the same thing's true. The smooth muscles are abnormally contracting, creating these spasms or constrictions of the bronchioles, causing your airways to close up. And so oftentimes you can take inhalers to open those up to relax that smooth muscle. And then, of course, you have lung cancer, right? So this is where you have a thickening of the lining of the bronchi. It closes up. Your cilia typically are lost, and so you can't actually keep your air clean. You'll start to see abnormal cells which start to invade. Tumors of those cells will start to impede normal function, and then it just goes down from there. So ultimately, it's kind of a terrible type of cancer, especially once the tumor sets in. And sometimes you may have to remove a lobe of the lung or a whole lung before it goes metastatic, which means the cancer starts to spread throughout the body. And this is kind of what it looks like. So essentially on the left is a normal lung. This is actually what a cancerous lung looks like, probably because of smoking. So you can see the amount of damage. It's very clear. Okay. And that is the end of chapter 10.